Hi, good morning. Welcome to Compilers, ece351. This is going to be our last lecture. In the last two lectures, as you remember, we're going over some more advanced topics in compilers. And the topic for today is garbage collection. Right? We're doing two topics about how a compiler makes something finite look like infinite. Last time we talked about register allocation. Today is garbage collection, memory management. Even so, it's the last lecture. It is something that definitely is going to be on the exam. So pay attention. I'm going to use an example from Beckett because it's fun. So there's a picture of Beckett. And if you don't know who Beckett is, you can look him up. So Beckett had a play, or has a play called Waiting for Godot. And this is what this example is modeling. What we want to know, what we want to pay attention to is we're going to draw our object diagrams to see what objects are available when. And we're going to look at what happens with this object, how should they be removed from memory. So we have this class, Beckett. Here, there's a main method. The main method calls act1, then prints waiting, act2, and then prints Godot. Act1 has the following code. We have two players in it, Vladimir and Estragon, also person, also different. And then they are connected to one another. Estragon is a friend of Vladimir, and Vladimir is a friend of Estragon. Okay. So with all of this, if we are to draw an object diagram as it is at the end of method act1, we have our PC. We have a function main. It has no locals. It calls act1. Act1 has two local variables, Vladimir and Estragon. Vladimir is connected to person. Estragon points to another person. And then the persons point to each other through the friend field. Something should not be any surprise. Then we're going to go into act2. Go like this. So act2, we have two new players, Lucky and Pozzo. They're also persons, and Pozzo is a friend of Lucky. There should be, and that's it, right? There's no other direction. Again, if we looking at an object diagram at line 22, what do we have? We have a function main. We have act2. Act2 has Lucky and Pozzo. Lucky is a person 3. Pozzo is person 4. And Pozzo friend is Lucky. So we have this connection in here. Again, should not be surprising. But the question is, what happens to this case? Right, this two person 1 and person 2 that were connected to local variables of act1, Vladimir and Estragon. Well, they're still somewhere in memory, right? Because we never explicitly deactivated them and deleted them. So they stay there and occupy space. And we want to somehow get rid of them. So what are our choices for doing this cleanup? Right? So we have a program that just creates objects and assumes that they somehow disappear magically when they no longer need it. But how does this actually work, and what are the different choices for this? Well, let's see. So our first choice is going to be just don't let garbage pile up. Right? So that means that you just delete things as much as as soon as possible. So how can we do this? Well, one way is we can make the programmer be responsible for this and let the programmer delete any unused object. Right? So this is more like C. I know the slide says C++ because you can program in C++ like this, but it's much less of an issue in C++ and a really big issue in C, where you have to explicitly call delete methods or free to deallocate. Have to call free to deallocate objects, And of course, if you don't, then the object will remain in memory. In C++, things are slightly better. There is an automatic cleanup of stack allocated objects and destructors that can be called. And so you can program carefully in C++, especially in a new flavor like C++11, C++14, C++17, where a lot of memory deallocation happens automatically. But in C, it's manual. And the benefit of it is that it gives the programmer a lot of flexibility. You can decide when to remove the object and how to engineer your system in such a way that it's done the most effectively, most efficiently. But it's very error prone because if you have to think also about when to clean up objects, you can make mistakes and forget to clean them up and leave objects behind. Now, another option is we can restrict our programming environment. So for example, we could say that we're going to allocate objects as we need when the procedure runs, essentially on a stack, but not necessarily on the actual stack of a procedure because that's a limited amount of space. Maybe we'll allocate on a heap, but we connect everything that we allocate to the stack. And then whenever a procedure terminates, we just clean up everything that the procedure has allocated. Now, this is possible for certain systems. So for example, in the case of embedded systems, it's often that the restrictions like that is placed because you want, in addition to good memory management, you want to have very predictable runtime. And memory allocation could be quite unpredictable because you need to find a free region, allocate it right into various data structures. And so one way to make it more predictable is to say, whenever a function runs, it just grabs available memory that's sort of immediately there. And whenever it exits, we just restore the memory, the pointer that says how much memory allocated to where it was before the function. So the allocation is very quick. The problem with this is, of course, that that is too restrictive for many of our programming tasks. It's often that we want to have functions that say allocate objects and then keep them in some data structures, and other functions operate on those objects, which will not fit this restriction. In something like an embedded system where something may happen periodically and some function comes up and that function allocates memory while it works and then removes memory, that's fine. But in many applications, this is just too restrictive. Now, another choice, which is getting more and more popular now, especially in environments where performance is critical, so where you want to have low-level memory management, but you do want to avoid the completely manual and error-prone approach, is to somehow require the programmer to indicate clearly a lifetime of an object or an ownership of each object. And in this case, the compiler will automatically insert the memory reclamation code. A system like this, the one that's probably most popular now that you may have heard, is a system like Rust. And if you ever tried programming in Rust coming from a different language, you'll see that one of the difficulties is that you have to be very, very aware of a lifetime of an object. So where an object begins its life, how long it's going to continue its life, if it has to live in some global data structure, how it's going to escape this. And as soon as you start programming more or less advanced data structures, like a graph is a good example, you'll see how complicated it is to stay within the system of Rust where memory is automatically reclaimed while trying to sort of do a usual data structure that you know. So a graph is a good example where it's very hard to assign good ownership because there's no direct relation. So there's not clear which object belongs to which other sub-object. Okay? But this is still a growing way to do things. And the benefit of it, of a system like Rust, is that at the end of the day, the program could be very efficient. It doesn't have a separate garbage collector that runs at some kind of time in the program and affects the program execution. So the program is more predictable. Usually it is more efficient. The cost here is that you may need to get adjusted to a given programming style. And in a few places, you can't really do anything but go back to manual. And so there'll be parts of your program in Rust, there are parts which are marked using an unsafe code annotation, where you basically left to your own devices to manage memory properly and then make sure it's deleted and whatnot. So there still could be some errors related to memory management, but they're restricted to things where unsafe is used. Now, of course, since we're working with Java, we're getting to this part, which is do an automatic memory management. And this means that whatever our execution environment, usually it's a virtual machine, periodically stops execution of a program and then looks around to see what objects are no longer necessary and automatically reclaims this object. This is called garbage collection. It's not pioneered by Java, but Java was sort of one of the first mainstream languages with garbage collection. Before that, there were lots of less popular languages with different forms of garbage collection. But there was always a question, can they be as efficient as, say, C and C++ for real-life applications, for enterprise applications? And Java was the one that sort of showed, yep, that's possible. It's much easier to program. There is a cost of garbage collection, but as we'll talk about today, there's lots of ways to improve garbage collection so that the cost is not that big. And it can also give you a lot of other benefits, like easier memory allocation, less memory defragmentations, things which actually may be more important than pure performance for a long-running server enterprise application. And of course, there's lots of other languages with garbage collection. So Python has a reference counting garbage collector, which we'll talk about shortly. That was probably before Java or around the same time. JavaScript, of course, has a garbage collection, and C#. So now nobody's surprised by a language with a garbage collection, but Java is really the one that took it mainstream. Now, why do we care about these things? Well, because memory corruption bugs are still a huge problem. If you look at vulnerabilities, so this one is from 2019, but not much has changed in the last 2 years. Is that almost a big chunk of vulnerabilities have to do with memory corruption. And this is memory corruption, really, I'd say mostly in C code. C++ code gets dragged in, but for two reasons. One is that people often program in C++ as they would in C. They just say, oh, it's a little bit nicer syntax. And because C++ code often interacts with C code. So you may have an application that is a C++ application, but it uses a lot of C libraries. And to interact with C libraries, it has to do memory management manually like in C. And so the bugs are likely to be in here. If you write C++ code using C++11 and things like std unique pointers, I'm not spelling this well. So if you use data structures like smart pointers like std unique, then your chances of memory corruption in C++ are actually very low. But C++ gets dragged in because it's exactly the language that's used when you have to interact with other C libraries. Right? And so conclusion is that it's been around, this problem has been around for quite a while. Whatever solutions we have, they're not really working. And so one way to deal with this is to move to just a different language. So move to Rust, where the behavior could be similar to C, but the compiler ensures that all objects are managed properly. All languages with garbage collection like C# or Java, where you do lose some performance or some ability to manage memory as you want in your source, but you gain a lot in safety. Now, this problem of managing memory corruption is actually really, really old. And this is from Tony Hoare's speech for his Turing Award in the 1980s. And Tony Hoare is a very famous computer scientist. You probably heard about him for many different reasons. One reason you may know him is that he is an inventor of quicksort algorithm for sorting, among many other things. He was one of the designers of the Algol 60 compiler, which is a compiler that influenced a lot of ways how we view compilers now. And he spent his life working on the problem of how to ensure that the software is correct. How do you reason about it? But this was about his experience with Algol 60. And he's saying that, well, initially they had, whenever you access array, they were using runtime checks to check that both upper and lower bounds are declared within the array. And then when they went and talked to their customers to see, how important that would be, because of course that has a fairly significant runtime cost. The customers, even by that time, already recognized how important this is, and they wanted that. They didn't want to remove this feature, even if it gives them better performance. But then this really wasn't picked up in the new language designers, and a lot of new language designers went for performance over safety, right? And we have languages like C, where you can access any piece of memory any way you want without any runtime checks. And if this would have been at that point an engineering discipline, like picking a language to build a system, then this really should have been, against a law, or at least against good engineering practice. But it wasn't, and that's where we are now. Okay, so this was a preamble to show why we may want to have garbage collection, because this is a way for a system to guarantee absence of certain class of memory errors, and it will have a runtime cost. It will have a fairly significant runtime cost, but we have to weight, performance that we can achieve versus the kind of quality we can guarantee of the system. So let's look at how to do garbage collection. The first way, this is sort of the most obvious way, this is what's implemented in Python, is to use reference counting. So the idea is very simple, that we're going to keep a count for an object based on how many pointers point to it, based on how many places it is used. And whenever the count of an object gets to 0, then this object is deleted. Okay? The problem with this is, of course, that if we have cyclic references, then the references will never get to 0. And this is a known problem. For example, in Python, you can create loops in between objects, and then these things will never be garbage collected. So we have this example in here. Let's just look at what's in here. So here we have the Vladimir and Estragon here classes, and because each one is a friend of one another, by the time nobody uses them, this one has a reference count of 1 because of this link here, and this one has a reference count of 1 because of this link. And then if we look at our second set of objects, Otso has ref count of 1 because it's only connected this way, and Lucky has a ref count of 2. One is from this assignment when it was assigned to Lucky, and one is from this assignment when it was assigned to the friend field. The problem is, of course, that because there is a cycle in here, even so there's no arrows from any of the local variables, the reference count is not 0, and we can't remove that object. So that's the problem with reference counting. It's easy to implement, and we'll look a little bit about how it's actually done. But we have to, we have this problem, and there's two ways to deal with this. One, like Python, you basically say that whenever you have such a case, That's it. We're just not gonna garbage collect it. We accept this as a limitation, but we keep it. And another way is to use something other than reference counting to well, something that's not as limited. Right. So I mean, this is just a joke to show you that, many times people come up with this idea that we do reference count, and you can go over and over and figure out all of the details. And then you're going to be hit by the cyclic data structures, which cannot be reference counted properly. Now, what happens, how reference count is actually implemented? Well, depending on what systems you're dealing with. So if reference counting is done as part of the compiler or part of the interpreter, as for example in Python, then every time there is an assignment, then first of all, an object, if a variable that is assigned into already contains some other object, that reference count is decremented, and then the reference count of an object that is assigned is incremented, and it's stored in a variable. So here, if we want to do x equals y, then the way this will be either compiled to interpret it is first we look at where x points to. If it's null, nothing happens. And if it points to somewhere, then we decrement its ref count by 1. Every time we decrement the ref count of any object, we check whether it is 0. And if it is 0, we call something to delete it from memory. After that, we copy do the actual assignment, copy object y into x. We now know that x points to a new object, and the object now is pointed to by y and by x. So we increment its ref count because there's a new reference now. Okay. So for example, if we'll see here on the right, if x was pointing to some object, we say reference count 1, and y was pointing to another object also with reference count 1. Then the first part up to here, we check the reference count of this object, we decrement it, we get it to be 0, and we delete it from memory. And then we take this object, object 2, we copy it into x, and then we go and increment its reference count. So its reference count is now 2. And so this object, basically, we have to get rid of variable y and get rid of variable x before we can get rid of that object. Okay. A compiler will also insert appropriate things, obviously, at the end of lifetime. So whenever, say, x and y go out of scope, they're not just forgotten, but a reference count is decremented for an object that they point to. Okay. It's easy to implement. It has a problem with cycles, but we can say, okay, we'll let the programmer deal with this. So if a programmer is not accurate, the program will leak memory. Not nice, but maybe not a huge deal. And if a programmer is careful, then they'll ensure that they never create cyclic data structures. And of course, if you want to implement something like a graph that has a cycle, well, then the programmer has to think how to do it without just doing pointers to objects. So for example, you can assign each object a numeric ID, and then when you want to point to an object, you just store an ID of which object you're pointing to, and then you can look up this object somewhere else. So the benefit is that it's pretty easy to implement. It's both fairly easy to implement automatically in a language. It's also a very common thing to use in a library, so in C and C++. One way to simplify memory management is to add this reference counting. It's pretty easy to get right in terms of implementation. And most importantly, it has a pretty good expected runtime. So forget about how much slower it makes your program doing all this reference counts. It doesn't require to stop the program in order to clean up garbage, right? So that means we have, if we run the program once, we run it twice, we see its runtime, it's kind of predictable. We know more or less how long every instruction will take, because all the reference counting and all of the object deletion is interspersed in the program code, always takes about the same time. The cost is we are not allowing cycles in our data structures. And this is not something that a compiler can easily point to a programmer. So it's up to the programmer to ensure that whenever they create their data structures, they don't have circular pointers. There is some cost in terms of time. We have to do this code that we're doing, the increase and decrease references in lots of places, sometimes in way too many places. So if you think that you, for example, assigning from X into Y, and then maybe Y is no longer used, so we're really transferring ownership from Y to X, then if you were doing it yourself manually, you would say, "Ooh, I'm transferring ownership. I don't really need to increment and decrement the count, because at the end of the day, it's going to be the same. It's just going to move from Y to X." But the system has no way of, the compiler has no way of knowing that. And so if when you program, you don't have special things like I'm moving an object as an operation, you just have assignment, and a compiler may end up inserting too many of this reference counting updates. And surprisingly, this adds up. Like if you think about how hard it is to do +1, -1 once in a while, if you think about what it actually has to do, so to add 1 to a field in an object, well, the object lives in memory, so you'll need to look up that piece of memory. You need to load that piece of memory into register. You need to do the increment. That itself is probably very fast. And then you need to store it back into memory. It's actually quite a few of assembly operations, and they influence memory, which means they're also going to influence the cache lines. And so there's quite a significant disruption on the program execution because of this extra out of band +1, -1 all over the place. And they add up, and it's amazingly how much slowdown you can add by not careful management of reference counts. And then the same about space, right? So it adds an extra field to every object. And again, you may think that's not a big deal. It's just going to be one integer. But for very critical code, this can have a big effect. If your object is slightly bigger than, with an extra machine word, then it's no longer may fit into a cache. And then accessing it, therefore, there's going to be interference between cache. And so now all of a sudden, what used to be a very efficient operation without reference count, where you just maybe load 2 objects, both are in the cache, and you're modifying them at the same time, ends up being a lot of flushing of the cache, going to main memory, doing the slow pass of accessing things. Okay, so there are costs, but it's very easy to implement. That's its main benefit, and it has with all of this, it still has fairly dependable performance. So if you care not just about your code running very quickly, but you care that it's that the runtime is dependable, it's repeatable, it's stable, then reference counting is much more predictable than other methods. Okay, so the next algorithm we have is called mark and sweep, and this is the first garbage collection algorithm that we're going to look at that actually takes care about cycles, and this gets closer and closer to what's implemented in Java. We'll go through several versions of it to make them more and more sort of practically efficient. So we're back to our example, and we're just going to animate what happens. So we assume that the compiler knows about, or the virtual machine knows about all of the objects which were allocated. And so it goes and starts marking objects which are reachable from current local variables. And then it will delete all objects which were not reached. So we're going to go through everything that's on a stack. In this case, we have Lucky and Pozzo. And then we're going to do just the depth first traversal of what's reachable. And every time we come to an object, we're going to mark it. And in this case, we're going to mark it color blue. And then after that, we're going to visit every object because we know where each object is. And then we're going to collect the ones which are not marked and delete them. Now, of course, when we do this, we have to make sure that the program doesn't continue running and allocating new objects, because otherwise they would escape our marking and we would delete something that was allocated after we started to mark. So we stop the program before we do this, and then we restart the program after we're done. Okay, so let's see. So we go and first we find what's on a stack, we color it blue, we then follow the arrows and we say, okay, we can get to from Lucky to person 3, that's blue. We go back, we go to person 4, mark that blue. We see person 4 can reach person 3, that's already marked, so we're done. We backtrack, and now we have everything colored in blue that was reached. We then run a sweep phase where we go through the list of all objects that we allocated, and we check which of them are marked blue. We find these 2 objects in red which are not marked blue, and we call free on them to delete them from memory. So simple, and deals with the problem of cycles. So what's the benefit? We have a low per object space overhead, so we really just need 1 bit, not a whole field to count references. And then when the program runs, there's no extra cost during running. What does it cost? Well, first of all, so far, our allocation and deletion are exactly the same as in C++, meaning that we maintain the list of free memory, the list of used memory. Every time we delete an object, we have to add its space into the list of free memory. If we allocate objects in certain order, we fragment our heap. So that's our cost. And then the time that it takes for us to run garbage collection is proportional to the number of objects in the heap. So for example, if we were to create a lot of objects and then keep only a few, and this is a very common common behavior in Java programs. You think about most of the code that you've done during this term, you're creating a lot of objects, and then you eventually keeping very few of them. And that means that being proportional in the number of objects in a heap is actually pretty bad, because the cost of garbage collection will be how many intermediate objects you've created, rather than how many objects you want to keep. And of course, it requires stopping the world, right? So that means that the behavior from the user perspective, the timing behavior, may be quite unpredictable. So the program will run, and all of a sudden, at some point, it will get stuck, or at least the user thinks that it gets stuck because it's running garbage collection. And this is specifically problematic for any kind of applications which are interactive to the user. Because imagine, you're moving your mouse, or you're clicking something on your phone, and then the program all of a sudden is doing garbage collection. And for this few seconds or milliseconds, it can't do anything. So you can't, it doesn't react to anything that you do. You move your mouse, nothing happens. You click a button, nothing happens. So that's a really, really big problem for interactive applications. Less of a problem for big server applications, especially if we have load balancing, and we can say, oh, one server is now stuck, and so we'll maybe direct request to another server. If it's stuck for a little bit and the request comes a little bit later for the user, the interaction mode is such that we know there's going to be all kind of delays for all kind of reasons, and a garbage collection is just one extra delay. But for interactive applications, this is huge. Okay. So to address some of those issues, there's another approach called semi-space copying collection. And what it tries to do, it tries to address this problem that the garbage collection the cost should be relative to how many objects you keep, rather than how many objects you have ever created and turned into garbage. So the idea is that instead of marking the whole space, we're going to divide our memory into 2 halves. So if we take a whole memory, we're going to break it into 2. And at any point, we're only going to use one or the other half. And the other half will be waiting for us to be used later. When we used up all the memory, we still stop the world. We then go and figure out all the live objects, and we do this just like mark and sweep by looking through all the stack objects pointed from the stack and recursively objects pointed by other objects. And then we copy the live objects to the second half of memory. And when we do so, we of course pack the object in such a way that we reduce any fragmentation that is there. And then we simply restart the program. So whatever was not copied from one memory into another, it's effectively done. Right? We don't need to go and explicitly write zeros where those objects are. We simply copy new objects in, and then we restart the program as soon as all of the new objects are copied. And then from this point on, new memory allocation is in a new half. And then whenever a new half fills up, we just go and say, oh, let's switch. Switch around. So let's look at an example here. So we're going to have our memory divided into a from and a to. And whenever we come to a place where we say, oh, we're running out of memory, let's do garbage collection. So what we're going to do is we're going to, like before, figure out everything that is on a stack. Go and mark objects which are reachable from the stack, in this case. And then we're going to copy them over into the to space. Right? So we move them from here into here. Now, this moving is not that trivial because so we have to take an object and it has some fields in it, it has some data in it. We have to copy it over into here. But it's also important that we update all the pointers. So for example, this pointer was pointing used to point here, and this pointer used to point here. And we need to go and carefully update them so that they point to the new space. So that means every time we copy an object, if an object has a pointer, has an arrow in it, then we have to know where to change it. So to change it to a new address. But once we've done this copy, we simply forget about the from space. We simply rename it into to, we rename this into from, and we restart the program as if nothing happened. Okay? So if here in the from space we had lots of dead objects, we never even look at them. We don't traverse them, we don't mark them, we don't touch them. We only traverse objects which are blue, the ones which are reachable from the stack. Okay, so we've done that part. And so let's look at what's the benefits. So one big benefit is that we're actually changing how objects are allocated after the program ran for a bit. And so we can defragment our heap. So if a program was allocating lots of small objects, creating, destroying, and at some point it got to its sort of steady state where most of the things that it needed are allocated and they're going to be used, we can stop the world, defragment the heap, stick these objects all together in memory, not worry about how we manage free space. It's not fragmented in different pieces. There's no overhead per object at all, right? There's not even a single bit. No effect on program execution. We don't add any extra statements to do any kind of reference counting. The work that we do is proportional to how many live objects we have. So if a program allocates a lot of intermediate objects, all we have to do is just give it big enough chunk of memory to begin with. And then it will not run out of memory until it's kind of got to its steady state. And then at that point, we garbage collect, only copies the objects which I actually used, forget about all the dead ones at zero cost to us. No problem with cycles, right? Because we copy all the objects which we want. And so we don't care if the objects that we don't want have cycles. And we can also do what is called a bump allocation, which we're going to look at later. Is just a way to allocate memory where we don't have to manage free lists. Okay, so there's a question on CampusWire that I keep talking about a compiler allocating memory, but isn't it the operating system that decides how to allocate memory? And how can a compiler enforce something to an operating system? And that's a good question. And so the answer is that both allocate memory, both the compiler and the operating system. The way this works is that an operating system provides a way to get memory to a process. So essentially, it allocates memory in pages and maps them to physical memory. A compiler then can decide what it wants to do. It can either forward the requests of the program directly to the operating system. This is, for example, how how something like C would work, and then the allocation is handled by the operating system. Or a compiler can pre-allocate memory itself and then gives this memory to the program. And this is, for example, how Java works. You've probably seen that in Java, whenever you run a program, you have to specify how much memory it can use. What is the maximum size of the heap that it can have? And the reason for this is because the compiler then goes to an operating system and says, ooh, I'll need that much memory, give it to me now. And then it takes that memory, divides it into chunks, and starts doing, whenever a program says, I want to allocate new memory using new, gives which chunk of it can use. And of course, the operating system is aware that programs do this. And so when an operating system gets a request, allocate lots and lots of memory, then it knows that, well, it doesn't actually reserve that much physical memory. It just remembers that, okay, that's what this program wants. And only when actual requests come to write to memory, that page is created. So you can have a program that says, I'm going to use lots of memory and I'm going to call a malloc and get lots of memory at once. But actually, you won't see like free memories reducing on your system. Yeah, and so this memory management is quite intricate. And if you move to a lower level language, again, like C or C++, what you'll often see is that a programmer is doing that instead of the compiler. So for example, in C++, it is extremely common and absolutely necessary to create your own pool allocators for small objects. So where you would, as a programmer, use a library or write your own library that will allocate from the C++ compiler a big chunk of memory, and then allocate small objects and reuse small objects in that chunk of memory. Okay, so let's go back to our costs. Of course, the cost of this is that we can only use half the space. But one way, again, a lot of this, like, so this is a fairly big cost, but in many cases, if we compare it to the other cost, and the cost is, let's not use garbage collection, let's make the programmer manage memory. And from history, we know that there's going to be definitely memory corruption problems. It's possible that this cost, even so it's a fairly big cost, half of your memory, it may be far less than a catastrophic failure. As I was describing before, that it requires that when you copy objects, you also update the pointers, because if something was in one address and you move it, then every other object that was pointing to that object needs to be updated. And so that can be a bit tricky. And of course, we need to stop the world. And so if the number of live objects is actually very large, then we'll have to stop the world for a long time. All right. And so now we come to the last version. And the last version tries to optimize all of the previous ones based on the actual common usage. So it's going to be a semi-space, but it's going to be an asymmetrical variant of semi-space. Asymmetrical means that, well, it's not symmetrical. We're not going to divide memory into two halves, to and from. We're not going to switch between to and from. We're rather going to divide the memory into a small part and a big part. And the small part will be called a nursery. And that's where we're going to allocate all objects, or all objects that fit in there. And whenever a nursery gets full, we're going to move objects from nursery into the old space. And then for the old space, much less frequently, we'll use one of the other garbage collection techniques. So maybe it's going to be mark and sweep. Maybe it's going to be semi space that we're going to divide them old space itself into two, but that's going to happen far less frequently. And so we can afford to do something that is a bit more expensive. Okay. And the key observation is that, as I mentioned before, that in Java, there's a lot of objects that you end up creating which don't live for very long. They're just there in order to help create other objects. And so those objects will just stay in the nursery. And whenever we have to do garbage collection, they're no longer live. So they will not get marked. And then we will not need to move them anywhere. Right, and I already mentioned that for the old space, we just do collection as before. So we're going to do an example. So this is going to be a small example, and then we do a longer example for this. So this is how it looks like. We have an old space, which has objects which have survived after some time, and we have nursery where we allocate new objects. So we run Act 1, and we had the 2 persons created in it. And let's assume our nursery is just big enough for 2 objects. So if you want to create 3 objects, some objects have to be evacuated. So we come to this point, to line 16. We need to allocate a new person, but the nursery is full. So we run our garbage collection. So we go and see for each stack variable if they point anywhere. They don't, which means there's nothing that we have to copy from nursery to old space. We clean nursery, and that simply means that, well, nothing, because there's no live objects in it, so we don't have to actually do anything. We just basically say, oh, nursery is completely free, we can use it. And then we start allocating our objects. So they go away, and now we allocate person 3 there, and we allocate person 4 here. Right. Now, it's important to note the pictures are sometimes misleading. So you have this 2 objects in red, meaning, in memory, there's information about this object. And then on the next slide, they're missing from memory. And it's not that we go and actually clean the memory or write zeros over it. It simply means that we update a flag that was telling us which bytes of the nursery are used, and we just set them to 0, saying, okay, all of the nursery is used. But the objects which were in there, the ones that are colored red, they're not actually colored red. They simply become, their space is simply now usable. Okay, and so that's it. So what are the trade-offs? Well, we still have heap defragmentation to some extent, because we copy from nursery to old, and then on old, we probably use a garbage collection that does defragmentation. The space overhead is somewhat low, because the nursery is only big enough for sort of most common small objects. We don't, again, affect the execution of a program except for the garbage collection time, so there's no extra counters added anywhere. Work time that we do is proportional to live objects. If your program creates a lot of objects and doesn't use them after a while, the garbage collection time is not affected by that. No problem with cycles. Whenever we stop a program, we don't do a complete garbage collection only for new objects. And if our nursery is small, that means we may do stoppages often, but if the nursery is small, it's going to be quickly. And we can also use bump allocation with this, and we're going to see this in a few slides, what exactly that is. Costs, again, we have to move objects around memory, so we have to do the updates to pointers, and we have to stop the world, because if new objects are created while we're doing the copying, we're going to miss which objects are live, which objects are dead. This is the form that's used in the Java VM that you're using, and this is sort of the de facto current garbage collector mint. So what we're going to do now, just to understand it better, is we're going to go through a bigger example. Now, there's code attached to this example, but it's not that easy to look at all the code at once. I'm going to show you the code, and then we're going to hopefully understand how the code works, and we'll just look at the object diagrams without looking at the code. The code itself is it's on page 18 of the study question. Let me go there. Okay. So this is the code that we're going to be looking at. It is, no, actually, I do want to start presentation mode. Okay. So it is FRPN. So F stands for our formula language, and RPN stands for reverse Polish notation. And this is simply a notation where the operands come before the operator. So it's like a calculator where you can do things like this: 2, 3, plus, and that means add 2 plus 3. And so it takes a string like this, not with arithmetic, but with ands and ors in our F language, and constructs a formula in the F language, simplifying it on the fly. So the important part for us to understand is how this main loop works like. So there's a function main. It prints something. And what we're interested is in this parse function. It takes an array of tokens and does the parsing. Now, what we really want to understand is how this loop works. And so what happens is that it looks at whatever is right now at the current token, and then pushes on a stack the appropriate expression. So for example, if a current token is 1, it pushes true. If a current token is 0, it pushes false. If a current token AND, so this is the important part, it creates an AND expression, popping the arguments from the stack, and then pushes back the expression that was created, but only after running the simplify method on it. Same for OR, same for NOT. Okay. And I'm not going to show you the code for individual expressions. It's the same as what you had in the labs, more or less. Yeah. I'm going to wait until somebody tells me that we are in sync. And then we're going to switch to looking at, so I'm going to refer to line numbers in this example, but I'm not going to be showing it. If you're on campus wire and you're following along, then just say that we are in sync. Okay, great. So we got that. So now let's go back to our slides and let's look what we're doing. So actually at this point, I don't want a presentation mode. I want my annotations to stay. Okay, it's not really cooperating with. Okay, so let's set the stage what we're doing. So we're going to run this program on the following input: X, X, and Y or not. So if you think about what's going to happen, we're going to first parse X, and we're going to parse X, then we're going to create an AND expression like this. Then we're going to simplify it into X because X and X is X. Then we're going to parse Y. Then we're going to create an OR expression, and we won't be able to simplify it. And then we're going to create an OD expression. This is what the program will do. And we're going to look at the objects that are constructed and when and how they're garbage collected. We're going to use a generational garbage collector. We're going to assume that the nursery is of size 5. Now, usually 5 would mean 5 bytes. But here, to make life easier to manage, we're going to use a different metric for size. We're going to assume that every field of an object has a cost of 1. And we're going to assume that an object has a header, which is also a cost of 1. So for example, an object that represents a variable, x, right? So this object will have a cost of 2. 1 for a header, 1 for a field. And we're just gonna draw the pictures to see what's happening. So let's look at this place. So we are somewhere in the program, line 32. Let me use a different color so it's better visible. We have our A that represents which token we are processing, and we're about to process the first token X. And this is what we have inside the old space. And the first thing that we do is we allocate a representation for X. If we allocate a representation for X, it ends up being in a nursery. It is right now size 2, nursery is size 5, so we have 3 more left in the nursery. Right, and we have our parser stack, so the slot 0 of the parser stack points to this object. That's how memory looks right now. One object in the nursery. We don't know if we're going to keep it yet or not, and an old space has everything from before. Next, we're going to go and parse this X. So that's next slide. We're now going to second X. It's going to be in stack slot 1. This is our second X, var expression 1. It's also of size 2, so 2 plus 2. This together is 4. Our nursery is 5. Perfectly fine, nothing to do, we still have space. The next thing that's going to happen is we're going to run our simplification. Right? No, actually, the next thing is we're going to create our end. So we're going to go for an end. There's nothing to simplify it. So here we are. So we got to the end token, this one. We need to create an object for it. Our nurseries had only one space available, so we had to do the garbage collection on the nursery. Both of the objects in the nursery here, both of them are reachable from something that's reachable from the stack. So both of them have to be kept. We copy them into the old space, here and here. We allocate a new object. This object is of size 3, so our nursery still has 2 left. It's an AND expression, has left and right field. They point to this, and that's it. Next thing that we're going to do is we're going to simplify it and then insert it into the parser stack. So we run simplify, and this is what the result of simplify becomes. So we run simplify, and the simplify for an AND expression says if 2 operands are equal, then we return the right operand. So this right operand is returned and is stored into the stack. That's what's pushed onto the stack. No new objects are created during simplification. Just a pointer to this object is given. And our simplification happened to return the right object. So that's why var expression 1 is the one that's pointed to from by the stack. That's whatever got pushed on. And the end expression is still there. We still have a local variable that's pointing to it. Next, we're going to go and parse y. So we come to parse y. Remember, this was of size 3. This is of size 2, so it still fits into the nursery. We parse it. We create var expression 2 with y as its variable. It goes into the next slot of the stack. And we're going to go and parse or. We come to or. And so here we have to now evacuate. Right? So we come to parse to construct an or object. There's no more space in the nursery. So we start copying objects which are reachable from a stack. We can go this way, find this object. So this one will have to be moved in here. And this one is not reachable by anybody. It will disappear. So what we expect to see in the next picture is we expect or in the nursery and var expression 2 inside old space. And var expression 0 is still in an old space because remember, we never collect garbage in an old space unless we run a garbage collection on the old space itself, which is not what's happening now. So we get to this point, we have 0, 1, and 2. And or was just created. It points here and it points here too. So it's an or between x and y. And we call simplify. Nothing, simplify doesn't do anything. So next we expect it to be inserted into the stack, and we're going to process not. Okay. So we've added it into the stack. No simplification happened, and we now going to point to the node. But finally, we got to the node. Remember, node is of size 2, or is of size 3, nursery is of size 5, so they still fit. We allocate node in the nursery. It points to the OR expression as its only child. The OR expression points there. That's it. And then the next thing is we insert node into the stack. So now node is in the stack, or is out because it was popped when we were creating a node. And that's it. We got to the end of that code. And so as execution continues, more and more objects from here will go into here. An object which were created temporarily, like the AND expression that we created and then simplified out, it never gets into an old space and it got deleted. And then once in a while, we would go and run. Once in a while, we would need to run some kind of garbage collection on the old space. And when we do this, we would discover that, for example, this is garbage. And that object would be collected, and everything else for now would be still retained. I'm going to pause and see if there are questions. As you've probably noticed, doing this kind of an example uses all of the program understanding that we've developed through the course. So you have to be able to draw object diagrams, understand how the code affects the diagram, and also now understand where the objects are allocated and how garbage collection affects the execution. So all of this is needed to do this example. And for that reason, this kind of examples are really good questions on various tests and exams. So I would study them and try and make sure that I can do them without the help of the solution. Now, one almost final thing is this bump allocation that I referred to several times. And this is an idea that if we don't have to worry about fragmentation, if we defragment the heap because we copy things around, then we can actually use a very simple allocation strategy. It's called a bump allocation because every time we want to allocate an object, all we do is we maintain where was the last object allocated, and to allocate the next object, we simply move that up. So this is just like allocating objects allocating anything on the stack. We just move the boundary between used and unused. So this is a pseudocode to just show you, to make this a little bit more concrete. So say we want to allocate n bytes. So what we do is we check if there is n bytes available in our current heap. If not, we run garbage collection. And we hope that after we've done garbage collection, now we have enough space. If not, there's extra code to deal with memory errors. But once we know that there is enough space, all that we do is we move the start of the heap, the start of the free space, by the number of bytes we need, and we return the pointer to where it was. If you think that your heap is sort of a space like this, and then you have maybe this is all already taken, and you saying need 10 bytes, and we just compute plus 10 and return a pointer to new memory. Depending whether we want it to grow up Go down. So the thing is that this kind of code can be implemented very, very efficiently, right? So the slide here claims that you can do it in about 10 assembly instructions. Now, why is that significant? Again, in Java, there's a lot of allocations of objects, and all allocations are on the heap. So having an efficient allocator is really important. And you can compare it to a typical allocator in a language like C++, where we don't have automatic memory defragmentation. So we can't, if we were to do this in C++, then we can never free memory, because whenever we need to free a region, so for example, say we have, some object that is in the middle here, and we decided to free it. Well, if we're using bump allocator, that's not going to help us because we allocate always from the end. And so if we have a free space in the middle, that doesn't help. And so for that reason, what C++ does is that it keeps track of free chunks of memory and sticks them into some kind of list, some kind of free list. And again, either that's done by a compiler or it's done by the operating system, or usually a mix of the two. And when the program requests space for an object on a heap, then you have to go and traverse this free list to figure out where you have a free space. So it's going to be way more than 10 assembly instructions to do. And you can either make it sort of simple, and then you at least fairly sure it works correctly, or really complicated. Then it can be somewhat efficient, but it's never going to be as efficient as a bump allocator. Right? Because here, essentially, this cost of navigating the free space and figuring out where it is has been shifted to the garbage collector. So the garbage collector will take that time, whereas in a C++, this time is spread out in the allocator. Now, there's one thing, the reason why sort of even so allocation in C++ is really complex like this. There's one sort of saving grace for C++, is that in C++, many of the objects are allocated on a stack, which is not allowed in Java. So what you would do in C++, for example, with our example for the end object, you would write your code in such a way that this end that you're creating and simplifying is allocated on a stack, which is a bump allocation. And it is limited small space, so it's good for small objects which die young. And then only when an object is constructed, you would use a copy constructor to propagate it onto the heap. Yep, and there's a question on the Slack. So if this is my bump allocator, how do you free? There is no free. Right? That's the whole point. A bump allocator is an easy way to allocate memory, but you can't free memory. So if you take a bump allocator and you combine it with a C++ like view of the world, they just don't work together because you can't free. But if you take a bump allocator and you combine it with a garbage collector, if you're using the copying garbage collector, then that's easy, because the way you free is you allocate, and whenever you run out of space, you run garbage collection. Garbage collection will copy all the used objects and into a new space, and then you'll know in this new space where your free begins, and that's it. You're now ready to go. Let's see if I've answered that question. Maybe I'll draw a picture. So the way bump allocator would work in combination with this with a semi copying garbage collector is that you have two spaces. So this is to, this is from, and so you start allocating. So you allocated one object, you allocated another object, you allocated another object, and each time you allocate, you just bump. And then some of the objects became free. So maybe this one and this one. So free meaning that they're no longer used by the program, but they're still in memory. Then you run your garbage collector, and the garbage collector does the copy. And so it says, okay, this object goes here. This object goes here. And now it says, okay, new allocations come from here. So you have another allocation. Now, after we've done the copy, we can forget about the connections. We can forget about everything that is in here. It's no longer there. And now we have a new allocation. And now we have a new allocation in here. Okay. Same with nursery. If we have a nursery, we bump allocate in the nursery. And whenever we run out of space, we propagate nursery to alt space. And maybe we discover that there's nothing in nursery that's actually used except for the last object. So we copy that in an alt space, and then we go back to the top of the nursery. That's it. That's the end of the last lecture. If you have questions, ask them now. Ask them on CampusWire. You know that lab 12, lab 12, yep, is due this Thursday. Also, by this Thursday, there's a request that maybe we can move the deadline to Friday. And I've been so lenient with deadlines that if people ask, I will do this. So then this Friday, lab 12 is due. And it's also the deadline for all the other labs. Or more precisely, we're going to take the commit for lab 12, and then we're going to rerun the tests for all of the previous labs and give you grades based on that. Now, I don't think I've explicitly said that, but obviously your grade for a lab cannot go down. So if you got a particular grade, say for lab 6, and now we run the test again and something fails and the grade would be lower, then the grade after term would be the maximum of the grade before term plus the actual grade. So you cannot go down, you can only go up. And the goal is that if you had some bugs that you may have not realized, or maybe weren't able to finish, or were not able to fix at the deadline, well, we'll let you fix them now, and we will take that into account. It's not an opportunity for you to go and start fixing things last minute. And it's mostly for the kind of things that you may have discovered when you did another lab and you said, oh, now I see where things were wrong, and you probably fixed it a long time ago. We're just going to take it now to grade. Unfortunately, it doesn't give us a lot of time for lab 12. So there won't be a space between like you submit lab 12, we grade it, and then you can fix it. So lab 12, we just take the way it is. Our pre-exam period is very compressed because of the online term. So we simply don't have the time to be able to grade it and give you adequate time to do anything about it. That's it. Our exam will be released December 10. Same thing as the midterm. It will be on Quest, not on Quest, on Learn as a quiz. I think I'm leaning to giving you something like 4 hours plus 1 hour to do it. So 4 hours for the test plus 1 hour if you need some extra time to upload all of the materials. But basically the same as we had in the midterm, just a little bit longer. That's it. Good luck. If you have questions, well, nobody has asked them so far. So if you have other questions, ask them on CampusWire. And that's it. Good luck.